Good morning friends. After the completion of 11.7 up to the 11.7 numerical of exercise, now next is 11.8. Now the threshold frequency for certain metal is given 3.3 into 10 is to 14 Hz. If the light of frequency 8.2 into 10 is to 14 Hz is incident on the metal, predict the cutoff voltage for photoelectric emission. It means we have to find out the value of stopping potential. Now here whatever the data is given, first the threshold frequency, that is denoted by F0. F0 is 3.3 into 10 is to 14 Hz. And frequency of the light F is given 8.2 into 10 is to 14 Hz. We have to find out the V0, that means the cutoff voltage or the stopping potential. Now we know the equation of photoelectric effect or the Einstein's equation for the photoelectric effect. So there is the maximum kinetic energy, that means the half mv square maximum is equal to hf minus phi 0. Now equation K maximum is equal to hf minus phi 0. But we know that maximum kinetic energy is EV0 is equal to hf and phi 0 is equal to hf0. hf 0. Now listen here, what's happened? We know that the K maximum is equal to EV0 and Y function phi 0 is equal to hf0. Using this value, we obtain this equation. Therefore, V0 is equal to h upon a common f minus f0. Thus, we obtain the value of stopping potential. H is 6.63 into 10 is to minus 34. F is given 8.2 into 10 is to 14 minus F0 3.3 into 10 is to 14 divided by charge of an electron 1.6, 10 is to minus 90. How we simplify this subtraction? 10 is to 14 is placed in both terms, so that is taken out of this bracket. So 8.2 minus 3.3 outside the bracket into 10 is to 14. Clear this? So thus we obtain the value of stopping potential is 2.03 volt. So there is the cutoff voltage. Again, the threshold frequency of a certain metal is given. Value of the F0 is given 3.3 into 10 is to 14. If the light of frequency 8.2 into 10 is to 14 Hz is incident on the metal, calculate the cutoff voltage or the stopping potential for photoelectric emission. So F0 given, F given, we require the stopping potential. Here we are using the equation given by the Einstein, or from equation K maximum is equal to hf minus phi 0. But we know that the K maximum is equal to EV0 and phi 0 is equal to hf0. F0 is the threshold frequency. Therefore EV0 is equal to hf minus hf0. Therefore V0 is equal to h upon E into bracket f minus f0. So this value we obtain, V0 is equal to 2.03 volt. Now next. Okay, now next numerical is 11.9. The work function for a certain metal is given, that is the 4.2 electron volt. Work function phi 0, 4.2 electron volt. Will this metal give photoelectric emission for incident radiation of wavelength 330 nanometer? Here the wavelength is given, lambda is equal to 330 nanometer. That means the 330 into 10 is to minus 9 meter. Planck's constant is 6.63 into 10 is to minus 34 Joule into second. And 1 electron volt is equal to 1.6 into 10 is to minus 19 Joule. Joule. Right? Okay. Now listen. Here we have to predict about that for incident light of 330 nanometer. The photoelectric emission take place only. For that purpose, we have to calculate the energy incident on it, total energy. Therefore, E is equal to HF, but the frequency is not given, wavelength given. Therefore, E is equal to Hc upon lambda. If the energy of the incident light is greater than or equal to the work function, in that case, the photoelectric emission takes place. Otherwise, not take place. Right? Therefore, the incident energy, the energy incident on a metal is E is equal to HF is equal to Hc upon lambda. Now listen, this energy is in Joule. But here the work function given in electron volt. Therefore, here we have to find out the energy in electron volt is equal to Hc upon E lambda in electron volt. H is Planck's constant. C is the speed of light, 3 into 10 is to 8 upon E 1.6, 10 is to minus 19. And lambda is given 330 into 10 is to minus 9 meter. Thus we obtain the energy in electron volt is 3.76 electron volt. That is the incident total energy. Here E is less than the work function. Thus the photoelectric emission does not take place. Because the condition for the photoelectric emission is that if and only if the incident energy is more than the work function. Work function is the minimum energy required for the photoelectric emission. If the incident energy is less than the work function, so photoelectric effect is not started. So here the photoelectric effect does not take place because the incident energy is 3.76 electron volt, that is less than the work function for given metal. Clear this? Okay. Now next is the 11.10. Light of frequency 7.21 into 10 is to 14 hertz incident on a metal. Now electrons with a maximum speed of 6 into 10 is to 5 meter per second are ejected from the surface. That means as the light of this frequency 7.21 into 10 is to 14 hertz incident on a metal. So what are the electrons emitted from the surface having the maximum speed is 6 into 10 is to 5 meter per second. What is the threshold frequency of photoelectric emission? We have to calculate the minimum frequency required for the photoelectric emission or the threshold frequency. Now frequency F is given 7.21 into 10 is to 14 hertz. Right? Okay. V maximum is given 6 into 10 is to 5 meter per second. We require the F0, value of F0. H is Planck's constant, 6.63, 10 is to minus 34 joule into second. Here the mass of an electron is also required. Therefore, F is equal to 9.11 into 10 is to minus 31 kg. Here we are using which equation? Equation of photoelectric emission. Maximum kinetic energy is equal to HF minus phi 0. HF minus phi 0. From equation of photoelectric effect or Einstein's equation, K maximum is equal to HF minus phi 0. HF minus phi 0. But we know that K maximum not given. Instead of this, we can take the half m square maximum because the maximum speed of the emitted electron given. And phi 0 is the work function is equal to HF 0. Therefore, our equation becomes half m square maximum is equal to HF minus HF 0. Here we require the value of threshold frequency F0 required. Therefore, we convert this equation this form, HF0 this side, so HF minus half m square maximum. We require the F0, therefore F minus m square maximum upon 2h. Upon 2h. So now F is given, value of F 7.21 into 10 raised to 14 minus mass of an electron 9.11 into 10 raised to minus 31 into V square maximum. V is given 6 into 10 raised to 5 bracket square upon 2, H is 6.63, 10 is to minus 30. So as we simplified, so we obtain the value of the threshold frequency is 4.74 into 10 is to 1400. So that much minimum frequency is required for the photoelectric emission for a given certain matter. Clear this? Way is in numerical, but here our concept about the photoelectric effect and Einstein's equation must be clear. In that case, we can calculate this numerical. First, note down what are the quantities are given, frequency of incident light given, maximum speed of a photoelectron is given. We have to find out the threshold frequency. So from equation, Einstein's equation for photoelectric effect, so K maximum is equal to HF minus phi 0. But we know that maximum kinetic energy is equal to half m square maximum. And phi 0, work function is equal to HF 0. And we substitute in this equation. So our equation becomes half m square maximum is equal to HF minus HF 0. But we require the F0. For that purpose, we take this term on left hand side. HF0 is equal to HF minus half m square maximum. Therefore, F0 is equal to F minus m square maximum upon 2h. Right? As we substitute the value, we obtain the value of threshold frequency as 4.74 into 10 is to 14. Now, 11th numerical of exercise. Light of wavelength 488 nanometer is produced by an argon laser, which is used in photoelectric effect. When the light from this spectral line incident on the emitter, the stopping potential of photoelectrons is 0.38 volt is found. Find the work function of the material from which the emitter is prepared or made. Okay. Now, first, whatever the data is given, here the line of wavelength, lambda is given, that is the 488 nanometer. That means the 488 into 10 is to minus 9 meter. Right. Now, the stopping potential of photoelectron is found, that is the V0 is 0.38 volt. Now we require the equation of stopping potential in electron volt. So that is as we multiply with E with E, therefore that is the 0.38 electron volt. We have to find out the work function. Therefore Planck's constant and speed of light is required. So Planck's constant C is equal, H is equal to 6.63 into 10 is 2 minus 34 joule into second, and speed of light 3 into 10 is to 8 meter per second required. We had to find out the work function for a given material from which the emitter is made. Here the light emitted by the argon laser having the frequency wavelength is this, is incident on a metallic surface, that means the photosensitive surface, that is our emitter. Right? So what are the electrons produced with the energy? To stop this electron, that much stopping potential is required. So what is the minimum frequency required, minimum energy required to produce the photoelectron? That means we have to calculate the work function. For that purpose, we are using the Einstein's equation. So from Einstein's equation, Einstein's equation is that K maximum is equal to HF minus phi 0. But we know that K maximum is equal to EV0. Substituted here, therefore EV0 is equal to HF minus phi 0. Here we have to calculate the work function, therefore phi 0 is equal to HF minus EV0. Now F is not given, therefore we convert the frequency into wavelength. Therefore work function phi 0 is equal to Hc upon lambda minus EV0. Now listen, here EV0 is in electron volt, there is in electron volt, while this term is in joule, So here the subtraction, we can't take the subtraction. For the subtraction or addition, the both quantity must be in the same unit. Therefore, phi 0 generally we measure in electron volt. And due to that result, the first term should have the unit of electron volt. So how we convert joule into electron volt? We have to divide this quantity by charge of an electron. Therefore, phi 0 is equal to Hc upon E lambda minus E0. That is in electron volt total. Now we substitute the value. H is Planck's constant 6.63, 10 is to minus 34 into C, 3 into 10 is to 8 upon 1.6 into 10 is to minus 19. Now wavelength 488 into 10 is to minus 9, and the EV0 in electron volt 0.38. So as we simplified, so we obtained work function is 2.16 volt, electron volt. Suppose we calculate in joule. Here directly we E divided by E also, and here the E is not multiplied at that time. So work function in joule is 3.46 into 10 is to minus 19 joule. Value of the work function in electron volt and joule. Here is again, here the wavelength of lesser argon is given, stopping potential is given, we require the work function. For that purpose, we are using the Einstein's equation. K maximum is equal to HF minus phi 0. But we know that K maximum is equal to EV0. Therefore, EV0 is equal to HF minus phi 0. Therefore, phi 0 is equal to HF minus EV0. Now, F is not given, frequency is not given, wavelength given. Therefore, instead of the F, we substitute the C by lambda. Therefore, LC upon lambda minus EV0. Generally, we obtain the value of work function in electron volt. Now, here the first term has the unit is Joule, second term has the unit is in electron volt. So, here we are not taking directly the subtraction of these two quantities. Both quantities must be in same unit. Therefore, the first term must be divided by E. Therefore, it converts into electron volt. So, this is electron volt, that is electron volt. Therefore, 2.16 electron volt. So, value of work function is 2.16 electron volt. Now, in Joule, there is 3.46 into 10 is to minus 19 Joule. Now, next numerical is 11.12. That is the similar to the, I think, the one numerical we calculate. Right? Now, calculate the momentum and de Broglie wavelength of the electron. This electron are accelerated through a potential difference of 56 volt. Right? For that purpose here, what is given data? Data is only the 56 volt. Accelerating voltage is given. Now, kinetic energy of electron. KE is equal to E into V. A into, right? Now, already we know the equation of momentum of an electron. Momentum of an electron in terms of kinetic energy, P is equal to under root of 2mk, under root of 2m. M is the mass of an electron. M is equal to 9.11 into 10 is to minus 31 kg. Kinetic energy is E into V. Therefore, we can write this equation in this form, 2meV. Substitute the value to mass of an electron 9.11, 10 is to minus 31. Charge of an electron 1.6, 10 is to minus 19. And V is given 56 volt. 56. If we simplify, we obtain the momentum of an electron is 4.04 into 10 is to minus 24. Unit is kg meter per second. That is the momentum of an electron. Now, second part, we have to find out the de Broglie's wavelength. We know that de Broglie wavelength is lambda is equal to H upon P. Lambda is equal to H upon P. P already we calculate. Planck's constant 6.63, 10 is to minus 34 upon momentum is 4.04, 10 is to minus 24. Right? Therefore, we obtain the de Broglie wavelength is 1.64 into 10 is to minus 10 meter. Generally, the wavelength is measured in angstrom. Therefore, 1.64 angstrom. So there is our de Broglie's wavelength. Now keep in mind for this numerical. Here calculate the momentum first. And second is the de Broglie wavelength. For the electron accelerated by the potential difference of 56 volt. Right? Okay. Here the electron is accelerated by the external electric field or the external potential difference. Therefore, due to the external potential difference, whatever the kinetic energy gained by the electron is equal to the charge of an electron into supplied voltage. Therefore, kinetic energy Ke is equal to E. Now we know that the momentum, relation between the momentum and kinetic energy, P is equal to under root of 2mk. Now kinetic energy is equal to E into V. Therefore under root of 2meV. As we substitute the value of mass of an electron m, EV is the accelerating voltage, E is the charge of an electron. So we obtain the momentum of an electron is 4.04 into 10 is to minus 24 kg meter per second. After obtaining the momentum, now Deprecation wavelength, where is the equation? Lambda is equal to h upon p. H is the Planck's constant divided by the momentum. We obtain the wavelength is 1.64 angstrom. Clear?